The next talk is given by Daniele on linear algebraic depth-first search.
Thank you. So this is joint work with my colleagues Upasana, Sridhar, and Meng at EMU. And I would start by observing how graphs are ubiquitous in many applications today, in many domains. Just to mention a few, we could consider networks, okay, where we might want to model network communication, or data analytics to determine information about large-scale interconnection or social networks. And machine learning, like where from graphs we would like to apply some form of convolution, like recent convolution neural networks. More recently, in the graph community, there has been effort in producing an interface which is based on linear algebra formulations, and which is essentially due to a couple of factors. One is the ability to separate concerns between writing the applications and the libraries. Okay, so we want to be able to have the possibility to express different algorithms and the possibility to compute building blocks for these applications into different, separating the concern of writing these two. And then the fact that writing linear algebra, we can take advantage of decades of expert knowledge that went into these libraries. Okay, so we want to combine these two components. And this has spawned many different interfaces and implementations, just to mention a few, the Graph Plus interface, and some of them being implemented in the Sweet Sparse Graph Plus or the C++ GBTL Graph Plus template libraries, and many others. Okay. The whole thing requires essentially to one of the aspects is that graphs can be represented in multiple ways. Okay. So, for example, we could take the adjacency matrix of the graph. The adjacency matrix essentially maps how nodes are connected to other nodes. So, for example, if we order our nodes from 1 to 4 in this example, the fourth node is connected to node 1, 2, and 3. Okay? Or the incidence matrix. Okay? So the incidence matrix allows you to map nodes and graph and the edges in the graph. Okay? So always based on this example, node 4 has 3 outgoing edges. Okay? And if we reorder the edges on the columns of the matrix, we can indicate whether they are outgoing or ingoing with using signs. And then there are other forms like adjacency or edge list to represent how these connections are made. Now, the linear algebra application essentially wants to take some of these way of representing graphs into account, and particularly those that allow you to express them in terms of matrices. Okay? And in this work in particular, we will focus on the adjacency matrix. Okay? Let me show you an example of how we could express a very classical algorithm like breadth of search using this approach. So we have the adjacency matrix of the graph, okay, and we have a starting node which we list as a vector. Okay, so the vector x says that we want to focus on node 4. Okay. Now to discover the frontier that we could traverse the frontier of the graph starting from node 4, what we can do is to multiply the adjacency matrix, the transpose of the adjacency matrix, by x. Okay, this would allow us to say that from node 4 we can go to node 1, 2, or 3. Okay, this is highlighted with the, say, orange edges here. And the moment DFS wants to essentially go further in this, in the search or in the ordering of the nodes, we can essentially take this information, put it back into X, and iterate further. Okay? Now, what about depth-first search, which is another classical algorithm? Okay. Well, it turns out that depth-first search is a little bit trickier to express using this kind of formulation. And to show you why, I would like to essentially take this example and see how this frontier is traversed. Let's take the BFS example that I've just introduced. And what we can notice is that BFS essentially tends to traverse the depth of the tree. We are taking multiplication, we would keep sorting the nodes based on the DFS traversal. And as you can see, the traversal reaches all the way down the leaves. Okay, so it's a very kind of linear way to traverse the graph. Now, the moment we go to DFS, what we notice is that this frontier moves a little bit more differently, less regularly than this. So, for example, DFS requires to pick a particular order and go all the way down to the leaf. Okay? So, therefore, the frontier that we see, so the sorting of the nodes, is done that first, and therefore the frontier of those nodes that should be taken into account to explore the graph further are kept waiting, in a sense, until we don't backtrack and reach higher up in the graph, these nodes. And that's one of the reasons why essentially expressing this using matrix operations has always been a little bit more difficult compared to DFS. So here I would like to give an idea of the approach that we propose in this work. We essentially maintain 3 different sets of the nodes that we encounter while we do the sorting. So we have those nodes that we label as ordered, and here represented in blue, the partially ordered nodes represented in red, and the unordered nodes, which are still to be explored. Okay? And we use an array representation to describe these sets. Okay, so we have the ordered nodes on the top of the array, the partially ordered in between, and the unordered nodes in the leftover. Now, every step that expands the frontier essentially selects one node and produces, determines a few nodes, in particular in the case of 2 nodes in the case of the binary tree, which belongs to unordered nodes. Okay, so notice that essentially the nodes from which we expand belongs to the partially ordered, okay, and the nodes that we want to attach to the frontier essentially belong to the unordered nodes. Okay, so the next step is requires essentially to do 2 things. One is to determine that the current selected nodes that we are using to expand the frontier goes into the ordered. Okay, so this is one step. And the next is the unordered nodes that we have found attached to this node has to go into the red region, the partially ordered region. And in a very particular order, okay, which is the one that would reflect the use of a stack in classical implementation. So essentially we want to permute these nodes within the array so that the next node that we pick is the one that we would like, for example, the one on the left in this case. Okay? So this can happen in a linear algebra fashion through the use of permutations. Okay? So imagine, for example, that we start from a state of the ordered of the nodes, which is given on the right in ST, vector ST, which says we have 1, 2, and 3 as an order, and we want to permute it such that we have 3, 1, and 2. Okay, so this can be done by using a permutation matrix, okay, which is also obtained, and the sorting is also obtained through the use of matrix vector multiplication in this case. The permutation matrix is obtained by basically stacking vectors of the standard basis in the order desired that we want to obtain. Okay, so in this case, for example, E3, E1, and E2, where these are vectors of 0 and 1s in the dimension specified by the index. Okay. Now, constructing the permutation matrix, the details about the construction are provided in the paper. Here, what I would like to essentially give is an intuition about one aspect of this construction, and it is that the permutation matrix P is determined at every step by taking into account 2 of the 3 regions. Okay? In particular, we just essentially this requires you to construct P by considering that the top part has to be unaltered. This is the ordered set part of the array, and the subpart that contains the partially ordered and the unordered are those that actually have to be permuted. And the permutation of P hat, which becomes smaller and smaller as we progress through the graph, or through the tree in this case, is basically determined by the fact that we know in which particular position, given the DFS order we want, the nodes have to go from in between the two steps. Now, we have been using in this example so far the concept of state of the order. Okay, that we are saying we have node labels and we represent at any step the order that they pick by using permutations on these vectors. Now, the moment we represent a matrix, we have this information already implicitly present in the adjacency matrix. So this very same order is reflected by the fact that we represent the adjacency matrix ordering the rows and the columns in a specific way. Okay? So this is essentially the kind of information that we would like to permute. Okay? Rather than representing extra vectors to contain the node, the labels of the nodes, we could, as we use the adjacency matrix to progress through the graph, also maintain the order that we want, the order that we encounter while we sort the graph, as part of the adjacency matrix itself. And notice that the moment we partition the array of the nodes, this also determine a partitioning of the adjacency matrix for this reason. Okay? So essentially we can identify the three regions within the adjacency matrix itself. Okay? Now this means, as a result of this, that we want to essentially permute the adjacency matrix. So differently than permuting an array or a single vector, permuting the matrix requires a little bit of attention. In particular, we would not be happy just permuting the columns of the adjacency matrix. Okay? To do a correct permutation, we have to take into account both columns and rows. Okay? So essentially, the permutation of the adjacency matrix from step t to step t plus 1 requires to use the same permutation matrix that we have constructed to be applied on the left and on the right of the matrix. Okay? Now I would like to address how do we extend this concept that we have shown with trees to essentially general graphs. Okay? In particular, general graphs present one aspect, that where nodes can have multiple predecessors. Okay? And what does this mean, considering our way to represent the sorting entailed by DFS? It means essentially one thing, that whenever we decide how to expand the frontier, so we essentially multiply by the adjacency matrix and determine the outgoing nodes, we can find these outgoing nodes now not longer only in the unordered part of the array representation, but also as part of the partially ordered one. Okay? So the permutation has to take into account the possibility that some of the nodes might be already being encountered and already being available in the partially ordered set. So one other aspect of this is that classically, if we imagine the sorting performed using a stack, this would typically require duplication of the information on the stack, essentially. So let's assume that we are now we've started from node 4, and we have progressed to the point that we are now at exploring node 2, starting from node 2. Okay? So node 2 was already encountered. Okay? And node 2 is connected to node 3, which also was already encountered as a neighbor of node 4. Okay? So the moment we include node 3 on the stack, and then we realize that node 3 has no outgoing edges, therefore we can consider it as we can consider 3 as part of the ordered set. What happens is that typically on stacks we would mark node 3, the node 3 already, which could potentially be already available in the stack, as visited. Okay, and this would allow us to essentially not repeat processing once we reach it the moment we keep popping. Our approach essentially does not require this, and is essentially analogous to say that rather than just labeling 3 as visited, we are essentially even dropping it from the structure in a sense. And therefore, we don't need to replicate this information within the array representation of these of the process. So this is let me summarize this work. This is work in progress, and this is represent a first look at how to perform DFS using the language of linear algebra. And I would say that the key concept is essentially that permutations play the part of sorting components. Okay, and therefore, the moment we want to apply sorting, we can do this by constructing appropriate permutations. Therefore, looking forward, one of our goals is to now proceed by looking how to extend current interface, available interface like Graph Plus that I mentioned before, in order to include this concept. And also to demonstrate that based on this we could achieve high performance by implementing the library components, the library building blocks, using HPC knowledge and expertise. And hopefully provide you at the next conference with more also performance results about this. Okay. So this is what I have. I probably helped getting early to lunch, I guess. I don't know how to speak, but happy to take that. And before this, I would like to acknowledge, of course, our funding agency for supporting our research. And but I would prefer to go back to the summary, so if you have questions, you can use this tool. Yeah.
Okay, so questions? Have you tried to measure any kind of feel for the performance? Will it be faster really to do it this way? It feels intuitively to me. It feels that this is slower. It's like doing. I've seen, for example, people doing the convolutions with matrices, and usually the results were not very satisfying. Do you have any indication that this might give some advantage?
So, to this respect, I would say one thing. What I've discussed so far is the specification of the drawing. Okay, so obviously, as already also mentioned by other previous talks in these sessions, the fact that we use a matrix does not necessarily mean a particular choice in storage, or the fact that we are multiplying does not reflect necessarily the fact that we want to multiply by a matrix. So this, for example, happens the moment we use sparse linear algebra, even for the computation that you have seen, like when we do DFS by multiplying by a vector, we use particular storages that can allow you to have high performance. And the multiplication is not necessarily the form of an n square, for example, representation of things like this. So there are tricks that you can pull to actually, by exploiting domain knowledge and some knowledge about the components in the expression, that you can include in your HPC solution. So for example, we might not even want to build P as a matrix itself. Being a permutation matrix, we know that it has certain properties, and we might just want to have those as indicators where we want to access information within the adjacency matrix. So I'm very confident because we have previous results in sparse linear algebra that tell us that this could be a viable way.
I was very intrigued by this when I read the submission, and I wonder if you view this as a way of laying down a future marker for when every computer we buy has a tensor processing chip in it, and it's an accelerator for linear algebra stuff. And just like you might be trying to exploit the GPU for general purpose computations, you might want to be exploiting the TPU for general purpose computations. This is a kind of step onto how we can squeeze more stuff onto those funky chips that people with special interest give us cheaply. Is that?
Yeah, definitely. So that's why I was mentioning that decoupling the concerns might help in this direction. So you could feel free even to express DFS using edges and nodes. And part of this work, which is not presented here, but is also in how can we actually leave users free to express themselves that way, and essentially provide a formal framework that systematically maps one to the other. And therefore there you could see a framework where, from a certain high-level specification, we can go to a linear algebraic one, which could map to HPC libraries and components, which might benefit from particular hardware stress that you mentioned. So definitely, yeah.
You know?
This is related to the permutation matrices. So if the matrix that you're going to apply the permutation matrix on, would that imply you would need many different sizes of permutation matrices? Number one, that's the first question. And number two, what if you were to perform multiple permutations on these matrices? Would that imply that you would have many, many matrices that you're doing matrix multiplication on? And especially with many of them sparse?
So the fact that we might have, so you're referring to for example, the fact that we have smaller and smaller areas that we want to permute, for example. So in that case, the permutation matrix would remain essentially of the same size as in the nodes. Just we would apply the construction of the permutation on very particular area of the permutation matrix. So we would take into account information of this kind. And the moment we proceed over iterations, for example, and want to multiply multiple times by permutation matrices, there it's debatable what is the right strategy. So one way could be, as we are, for example, using in this example, the possibility to just keep permuting the adjacency matrix. Another way could be we keep the adjacency matrix, but we essentially multiply and accumulate the permutations by essentially multiplying the permutations all the time, and therefore updating the permutation matrix in a sense. So there are different ways that one could proceed in this direction. Therefore, but it's not, let's say, necessarily related to the fact that we need to maintain multiple permutation information at once. So we could attach these to different entities in the specification, either the adjacency matrix or the permutation matrix itself.
And what if you were doing something more, that the permutation you were doing is a pretty regular one, but what if it was very complicated and each component was doing different permutations? One row was doing it by one, and another was doing it by three, and then doing columns, and maybe it was three-dimensional. How would you even invent the permutation matrices to do it?
So these, I think, would be something to study, to explore based also on the particular application. So here in the paper, for example, we point at particular ways of building this particular permutation matrix for the DFS problem. Okay? So obviously, the permutation matrix might depend on the application, and therefore it's difficult to give a general, to provide a general framework on how to build the permutation matrix. But definitely, these would be a problem-dependent aspect of the computation, I guess. So yeah, I hope this answers your question. I don't know if. Okay.
So I have a question. So it seems that in a sequential implementation of graph traversals, you would use a cube, right? So here for the parallel kind of version of DFS, you use a stack. Is there any greater insight into that difference? Or?
No, so that's actually an interesting aspect. So this means essentially that previous BFS implementation would actually model the queue exactly in an algebraic way. And also we have some work where we can show that we can also consider queues with priorities, for example. So this is a very interesting part, because how do we model what classically is regarded as a stack-based operation? And I think the permutation plays a role in that sense. And so this allows us to increase the framework and the possible applications that now we can include in these kind of formulations.
You had another, you mentioned that this thing with not having to, you had multiple items, the same things on the stack, and that you could avoid processing that, but somehow you need to mark that you shouldn't consider that. Are you traversing the entire stack?
No. So, okay, this actually is something that then I should be more clear about.
Okay.
So this was not to say that we are implementing this using a stack. So here I just wanted to show in parallel, in a sense, how our approach would, reflect the classical implementation based on the stack. So in the stack, you would have to, replicate this information, mark it as visited, and not in order not to alter the semantic of the stack, you, in principle, should not go and deal with elements within the stack without copying whatever is in front of it. In our case, it's like we have the possibility to move within the stack and get rid of some of the elements, in a sense, by using this approach. But we don't replicate, because the array representation is in the number of the nodes, and it maintains that size, that property.
So actually I have a final question. So I noticed that you, since some of the since it's not directed graphs, you don't have the pointers back from unordered nodes all the way to ordered nodes. But if you go with directed graphs, the situation might be different. Is that true?
So there are the way you would so the relationships between the different sets. In the general case of graphs, is the most general in a sense. So there are relationships possibly between all sets. Okay? But the way nodes move from one step to the other is essentially based on these exact semantics that we discussed. So there's no direct jump between one to the other. You typically first part in passing to the partially ordered, then you check, you have to see whether you have other nodes that you are connected with, and if it's not the case, then you move into the ordered one.
But for directed graphs, you might have something going back, so you have to.
So do you have a particular example, like?
So I was just thinking that if you go, the frontier might not have considered those things that will later on point back to the root, for instance.
Oh, yeah. Well, but in that case, that's exactly what this mechanism allows you to do. The moment you don't process the ordered nodes anymore, they are not able, in a sense, to come back again. So all the partially ordered sets would be filtered out. So in the paper we show a more general example where there might be this possibility. And the way you get rid of this is by essentially pointwise multiply the array representation, if you want, with only the forward nodes. So even if you would get something that now is part of the ordered nodes, you just don't consider it because it's already part of that set. Therefore, you just keep checking smaller and smaller sections of the array representation, looking forward only, essentially.
Other questions? Otherwise, let's have lunch then. Thanks to the speaker again.